Hello, I'm Luc Duponchel, and I'm going to present you some of the ideas behind my library, which is written in Haskell, called Program Description Based Programming. You see the logo here. There's much ado in programming about the difference between pure programming and, well, impure features that you can also do with your programs. Well, like you see here, it's all about describing programs, and there's really nothing wrong with describing effects as long as you don't execute them. So as long as they are not happening. And that's a little bit the idea behind the library. Maybe it's interesting to compare this with this picture here. It's a picture from a grid, and actually this is not a pipe, right? It's a description of a pipe. And much in the same way, if somebody would actually make a picture of an explosion, well, looking at that picture won't harm anything. It's the actual explosion itself that is an effect that is maybe harmful. Okay, so let's move along. I have 1, 2, 3, 4, 5 versions of my code, and I'm going to start with the first one, which is the so-called expression-based one. You see here factorial expression. The running example is indeed the factorial function. So let's move along and let's uncomment some of the code. I'm going to make this a little bit. Voila. So, here is our first version of factorial, and maybe I should also write here factorial. As the first version. Factorial is a function which, given a z, by the way, I'm using the American pronunciation of the letter, not z but z. And the first thing which I would like to say is that such a function is defined using an expression, and this is the right hand side, the expression defining the function. We all know how to define factorial. The most important thing to note here are those keywords here, and indeed those expressions can make use of if then else based logic. Maybe it's interesting to run this thing. So everything is loaded. Factorial 10, and you will see the right result. Okay, so nothing special about this. Let's move along. In this version, you now also see those blue keywords, let in, actually 2 lets ins. The second version exposes the fact that expressions can also make use of let-in based local values. For example, I just declare this boolean here as a local value whose value is the result of evaluating expression z is 0, and so on. Here recursively I'm using x as the factorial of y, where y is z minus 1, and then we do the right multiplication and return the right result. Okay, so let's try that one. no big deal. So we have two important language constructs here, if then else logic and let-in based local variables. Here's the big trick. Those language level let-in based local variables, well, I call them values because variable, it's a little bit tricky. A variable is mutable, a value is immutable, and we are only using immutable stuff. We can replace them by library level bind and result based local values. What's binding? Well, binding is actually the opposite of applying. So instead of applying a function z to y to an argument z, we actually bind the argument to that function. One nice advantage of this is it reads nicely from left to right. And we also have a trivial result function that just returns its argument as a result. And it's almost algorithmically that we can replace this function definition of factorial by this function definition of factorial. First here take this expression, result c is 0. I bind the result of evaluating it to a local variable b, a local value b, which is then the argument of the next function, which is this thing here. So if b is true, then I get result 1. Otherwise, I'm going to take this expression, evaluate it, bind it to the result, to the value y, which is the argument of this function, and so on and so on and so on. It's almost literally translating the let-in thing by the result binding. And then we have factorial 3 here, and it will produce the same result. Excuse me. What's wrong here? Okay, I already had it. So that's the trick. What made it fail? And let's run it exactly the same. Okay, so what's the next step? The next step is to come up with computations. So we are going to replace the expressions by computations. How are we going to do that? By actually specifying the essence of expressions. And what is the essence of expressions? Well, the essence of maybe more precisely of evaluating expressions is that they eventually yield a result, and the result actually kind of encapsulates a value into a computation yielding that result. Another essential ingredient of expression evaluation is that we can bind the result of evaluating a sub-expression, so to speak, which is this here, to a continuation. So in fact, when the sub-expression has been evaluated, the sub-expression, the evaluation of the outer expression continues with a continuation that uses the result of evaluating the sub-expression in order eventually to yield the result of evaluating the global expression. Of course, many of you will recognize here the definitions of a monad, and indeed what I will call a computation, and what also Eugenio Moggi and other people called computations, are also of course mathematically known as monads. So this is indeed specifying, or maybe if you wish describing, two computational capabilities. And computations, I will use the vocabulary to execute computations rather than evaluate them. Evaluating is what we do with expressions. All right. So now is the nice thing here is that we can use exactly the same definition. I'm not going to go in all details, but once we can bind and we can result, and okay, we can do that for anything which has equality and which is numeric. We can define our factorial 3 in exactly the same way as we did here. This factorial 3, okay? Result bind it to b, if b then result 1, result c minus 1, bind it to y, exactly the same kind of stuff, okay? What is the most important thing here is, let me first say some comments about computation descriptions, because in fact I would like to stress that it's more about computation descriptions than computations. They generalize expressions. Expressions are evaluated, expressions are pure. Computation descriptions are executed. Computation descriptions describe impure effects, but the impure effects happen only when the computation descriptions are executed. Those descriptions are also operational in nature. So they expose a sequential execution strategy, like first you execute this computation, bind its result to the continuation that executes this computation, and so on. So they are rather operational in nature. They also promote or actually use open box reuse, because you know you can think about result z minus 1 as a box, but the b that follows is actually the content of that open box, so you have to open this box in order to see what's in it. Here's a little bit of negative news. They are somewhat complex and therefore inherently difficult. Humans can only deal with a limited amount of complexity. And being confronted with this inherent difficulty, over and over again, isn't really fun. And because they are difficult, they are also error prone. And in fact, you may not have noticed, but my factorial 03 definition had a bug. I don't know if you can see it, but actually the bug is here. This y here should be a z. I did it on purpose, of course. The point that I want to make is that all those values, so those arguments that are have been given names like y, x, b and stuff like that, it can be confusing, maybe not in such a simple definition like here, but in more complex definitions it could become confusing. And let's replace it with the correct one, which is this one. Exactly the same, but with a z here, okay? Next. We can't really do a lot of things with it. Maybe I should also again write this here. So here's my factorial. Can't really do a lot of things with it. It's just a description, okay? It's programming to an interface, so to speak. There is no implementation at all. We specify things, we describe things. So let's go for an implementation. And of course, the simplest implementation you can think of is just the identity. And let's write it here. So I define a new type, IDZ. And ID is a computation that just puts a Z into a box, this ID box. And how do I execute it? By just extracting the Z. Okay, and I have to declare how ID is implementing the results and bind computational capabilities, but they are completely trivial, all right? So what to do next, apart from just doing this copy paste so that my comments are empty. We're going to load everything, and now we're going to load the computational one. And maybe it's interesting to do something like computation description. Is factorial. So now we have a computation description, and maybe you can look at its type. It's indeed this thing here. So nothing has been resolved yet. But of course, we can also run the computation description. I have a little problem here. Shit. What did I do? Oh, it's execute, excuse me. Execute. And we get our value. I'm sorry. Okay, so let's switch to functions. Same start. But since we are working functionally, I'm going to define helper functions. So, what are my helper functions? Well, maybe the most important one here is C2Z, which is the identity. I like those typeful names. They are somewhat in sync with theorems for free. There is only one reasonable function that for all Z goes to Z again, that's the identity. Is 0, I'll define that function as well. I define the constant function 1, I define subtract 1, I define multiply, by the way as a function of 2 arguments. Then I define this trivial function that is the identity as well. And actually the functions here, those helper functions, they are the atomic functions that I'm going to use. And I'm going to somewhat trivially define versions with an underscore so that we see which are the real functions that I'm going to use in my factorial program, like here, In factorial itself, I will also use it with write it with an underscore. Maybe not the best convention, but just to see the difference with the other functions I've been writing. So how can my factorial now be written? Well, if z is 0, then I'm applying 1 to z, and so I'm returning 1. Otherwise, I again have this let in. I'm letting y be factorial 0, 1 applied to subtract 1 of z in the multiplication of z and y. Okay, maybe I should write here again factorial 0, 1. Let's now load the functional one. Seems to work. Okay, so maybe this thing should be interpreted like, okay, functions are functions. I will tell more about this later. So that seems to be an important statement, which is completely trivial. But let's now take another one, which states that functions can sequentially be composed. So here's my sequential composition. I do it in the other direction than you may be used to, but once again, the slight advantage of doing it that way is that you can read from left to right, so z to y and then y to z, which is cancelling, so to speak, the y. It's also important to note that the z, which you have here, is not available anymore in y to x. It's gone. But anyway, I can now define another version of factorial that is using sequential composition like this. Alright, so that's the first step, and you already see that now we see z here, we see z here, we see z here, okay, and we see two values z and y here, but that's because we have our local value y here. So let's deal with that local value. What's the magic behind local values? Well, the fact that you can construct. Let me copy paste a little bit. What do I mean by construction? Well, you can assemble two values to get an assembled product value, and I'm going to define the type c and y as just the tuple zy. If I have two functions, z to y and z to x, and applying them to one argument can be done by what's called unfolding both to the tuple z to y of z and z to x of z, and actually I prefer to use and as a synonym of unfold product. I'll do this away. Now, what is the relationship between those products and the AND operator and local variables defined using let in? Actually, a special case, if you use the identity, using the identity also leads to special cases. Let us define local variables using our library level let instead of the language level let. So we have to read this as follows. If from a z I can produce a y, and from a z and a y, the y being produced from the z, I can produce an x, then of course from the z I can produce an x. And how do I do that? By just here, remember that sequential composition was forgetting about its argument. What I will do now is I won't forget about the argument. I do here my function, but I remember my original argument, and then I just use the z and the y to produce the x. Okay, so let's now write factorial 3. Before doing so, actually, I would like to give you a somewhat difficult, by the way, exercise which tells you that construction, so making tuple, so to speak, is completely equivalent with defining local variables. We will do that with exercise 1. But before doing that, and in fact we are not going to do that, you are free to try to do that yourself. Let's define our new version of factorial. So we still have our if then else, but now I have my let, so I'm going to produce my new local variable, which I obtain from applying factorial 2 to the result of subtracting 1 from my argument, and then adjust to the multiplication. Maybe this is not really very readable, but with a little bit of syntactic sugar, might be a little bit more readable. I'm just defining the completely trivial in, which corresponds to let, and then you can think about, okay, let, and here you have a new local variable defined by applying what I've highlighted to z, and as a consequence I have two variables, and I can use them in this multiplication. Okay, let's use 4. And let's do factorial 10, still works. Okay, so we've got rid of the let in. Let's now try to get rid of the if then else. We do a similar thing, but now we are using sums. Or conditions, just like we used construction or products. So we need a sum type, which is z or y, is on the left a z, on the right a y. Just like I can unfold two functions as a product, I can fold two functions from a sum, and I call that OR. OR is in fact powerful enough to define our if. So if I have a W to be, so a predicate, and I have a true case and a false case, then this definition here will enable me to implement if then else logic, where the magic is done by a very simple function, W and a B to a W or a W. And in fact, if the Boolean is true, I put my B on the left. If the Boolean is false, I put my W on the left. If the Boolean is, I just have to repeat. If the Boolean is true, I put my W on the left. If the Boolean is false, I put my W on the right. Good. And in fact, That is what allows me to branch to the true case or the false case, because I either do the true case or the false case depending on where I've put my W. Again, I can use a little bit of syntactic sugar. With a trivial then and an else, and then my factorial reads like if. And here's the most important thing, it's completely point free. I don't have values anymore, well, only function values. So if my argument is 0, the result is 1, otherwise I have my local variable which I'm using in my multiplication. Right? So maybe just like before, let's replace it by 5. And it just works. So now I have a point-free definition of my factorial with the library level if then else and the library level let in. Alright. Actually, just like with products, condition is equivalent with if-then-else logic. If-then-else logic seems to be a special case of this sums of this condition, but actually it has the same power of expression, much in the same way as defining local values, which seems to be a special case of construction or products, has the same power of expression. And that's another exercise. So here we go. We have now kind of seen what the essence is of, well, point-free functional programming. Namely the fact that functions are functions, completely trivial, that we have sequential composition, that we have construction, and that we have condition. Alright? Actually, I'm not at all the first one to see this. John Bacchus, Turing Award winner many years ago, implemented all this in his language, FP. The difference being that I'm now doing everything at the library level, which gives me the following possibility. I can generalize just like I generalized functions to computations. I can now generalize, just like I generalized expressions to computations, I can now generalize functions to what I call programs, or maybe better, program descriptions, right? Because they describe things, they don't do anything. So here we are. What was the essence of point-free functional programming? Well, first of all, I specify or describe that programs are functions. I'm using the to identifier for a program, so that I can write z to y. So any function from z to y is a program of type z to y, with then 2 as the name of the program. Of course, then I also have an identity. Much in the same way, I have composition. So I can compose, if I can go from z to y and from y to x, and I can go from z to x sequentially. The construction capability and the fact if I can from a z produce a y and from a z produces an x, then from a z I can also produce a y and an x. Alright. And then again, the same definition of local definitions. It's really exactly the same thing. And then the last programming capability is the fact that we can make if then else logic. We can do if then else logic, or we can do condition-based programming with similar thing which I've done already, but the here is a specification or a description. If from a y I can come up with a z, from an x I can come up with a z, then from a y or an x I can also come up with a z. With the same trivial things here, I can define my if. Okay. Now look at the types. They are kind of explicit. For example, in the if I have predicate kind of program, and program from y to z and another from y to z. Then I can go from y to z. I actually think, alright, that's true, yes. With the true case and the false case. Exactly the same thing. Okay, what can I do now? Well, I can again write my factorial. So like before, I have my helper functions. Z to Z was already defined above, the identity. I have my helper program descriptions. Now they are not functions anymore, they're program descriptions. From Z to bool, from Z to Y, and so on. They're kind of atomic programs, programs that we don't really want a lot of flexibility with. They are functions that are used as programs. Subtract 1, multiply. And I have plus or minus exactly the same definition using a program description of factorial 5 here. So factorial 5, if I have all my programming capabilities at my disposal, I have a type that is numeric and knows about equality, then I can define if is 0, then 1, else let's subtract 1 in multiply. Well, the only by do I say plus or minus exactly the same. Actually, it is the same. So it's exactly the same. Maybe up to the underscore here, I guess. Okay. So you can of course write this here. And let's see if at least if it compiles. So program. Okay. Now let me first do some remarks about program descriptions. First of all, they generalize functions. Just like expressions are evaluated and like computations are executed, program descriptions are run, so to speak. They run as, well, basically they always run as some type of functions that may become more and more complex depending on the programming capabilities that you want to be able to use. More about that later. Just like computation description, program descriptions describe impure effects, and impure effects only happen when the program descriptions are run. More importantly, well, it is important, but also very important is that they promote closed box reuse. We don't open them before using them. As a consequence, they are less complex, but maybe somewhat difficult. I think this let construct has some difficulty with it. But hey, understanding this difficulty once and for all is really big fun, I think. Remember that always being confronted with the same inherent difficulty is, well, not fun at all. I do agree that eventually, with all those local variables, we get some kind of, well, environment, so to speak, of local variables that is somehow tedious to deal with in a point-free way. But I would like to quote Eric Mayer here, who says like a good programmers write baby code. And so my experience is that the local variables that you need, well, if you say, so to speak, need like 5 local variables, then maybe your program is not simple enough, and you might have to split it up in 2 other ones that you combine with the combinators I've just presented. Alright, so here we go. Now we can't do anything with it because we are working with program descriptions, so let's define some implementation. And what are we going to define as implementation? Well, just normal functions. Just like we used the identity box for computations, we are going to use normal functions for programs. And really the new type here, normal function zy, is a normal function. And if you run it, it's just a function from z to y. The simplest thing you can think about. And you don't have to be a rocket scientist to define the capabilities, the implementation of the function capabilities, the composition capabilities for normal function, and so on. All right. So we're done. So let's load this. Still works, and let's define program description is factorial. All right. So what is the type of the program description? Well, the one you would expect. Have all these capabilities, and then it's going from z to z. Well, it's not using infix, but you see what I mean. So now I can run my program description. Let's call it runnable. Still nothing is happening. Is run program description. And let's look at the type of it. And indeed, yes, that's just a function, right? So my runnable program description, I can just give it 10 as an argument, and now actually it's running. But I'm going to show you something else. What is happening if I'm running -1? Oh, this seems to be problematic. It's in an infinite loop or something. Indeed, I didn't take into account that maybe I can feed my factorial with negative numbers. So we are going to do something about this. We have to handle this, well, how would I say, effect, this fact that the program fails in one way or another. And we are going to do it in the most simple way we can do it. No complex failure handling involved. We are going to just do the simplest thing that's possible. And here's now the benefit of separating programs from program descriptions, or computations from computation descriptions. Until now we have kind of designed a language with some language primitives, like the if then else, the let in, and the sequential composition, and then, but we can just extend our language with whatever we want. And that's what we are going to do in the next session. We are going to add failure handling. And how are we going to add failure handling? By just copy pasting exactly the same thing which we had already, but by adding this extra programming capability that programs can fail. Here it is. So that's the beauty. If we want to be able to do more, like maybe failure handling, handling state, doing things in parallel, you name it, we just extend our language. So we did now with an extremely simple extension. We also consider failure as a program. Okay? One extra programming capability. And we can just continue like we did before, just copy pasting, believe me, the same thing up to one detail, that now we, with our new language that also has failure handling, I can write a more sophisticated factorial that first tests if something is negative. Of course, is negative is then also one of my primitive atomic programs, so functions used as programs. But if it's negative, then, well, I'll just fail. It's a failure. Otherwise, I just do what I did before. And in fact, I could even reuse the previous factorial. All right? So if you really want to do that, you could reuse the previous factorial and call this like safe factorial or something like that. Okay. So we need an implementation. And what is the implementation? Well, the implementation is going to use the maybe data type from Haskell. I'm going to define my failure handling functions as functions that when I run them, or if I make them runnable, maybe that's better, they just give me a z that is a function that transforms z maybe to a y. So either it will just give me a y or it will give me nothing. And once again, and that's a little bit more tedious than what we did before, but when we are now defining the function capability, the composition capability, the construction capability, or the condition capability, and by the way also the failure handling capability of this implementation, the implementation of the failure handling functions, we have to be a little bit more creative, but we have to do it once and for all. What would normally be code that you always repeat in your application code at the application level, we write it now once and for all at the library level. So for example, the function will just do the function. Composition will, well, here there is a maybe primitive from Haskell that I'm using to say that, well, okay, if it fails, it's a fail fast maybe composition that I'm using here. The construction, okay, a little bit of pattern matching, maybe my left one is already a nothing, then I give up, also kind of fast failure. Otherwise, if the right one gives me nothing, I give up with nothing, and if both are not nothing, then I just return the tuple. Condition is even simpler, it's just a full sum, and so on. And what's failure handling? Well, it's completely trivial failure handling, which always gives me nothing. Okay. So, if now I'm defining my factorial as this factorial which I wrote using failure handling capabilities, then I should be able to handle failure. So let's do that one. Once again, I'm going to define my program description as factorial. I'm going to define my runnable program description as this thing. Maybe again look at the type, and now it should be one that maybe gives me a results. And we run it. So we run it. Let's first do the normal one with 10. Well, okay, don't worry, the 10 can also be written like this. It's just the right result, or with -1 it gives me nothing. Okay, thank you for listening.